Hello, in this video, I'm going to explain abstraction. What is abstraction? In mathematics, abstraction is broadening the meaning of previously defined mathematical objects by collecting their common properties. For example, when we first learn about the concept of a vector, we are taught that it is something like an arrow. However, as we delve deeper into the mathematics, we realize that a vector is an object that satisfies specific properties such as vector addition and scalar multiplication. In other words, a mathematical object is defined by satisfying a set of its properties, and this is how mathematicians use abstractions. Abstractions also exist in programming. In programming, abstraction is to define a type not by its actual form of data, but by the function called methods that type must possess. For instance, we can define an abstract type with the common property of addition shared by integer and floating point types. By using such abstract types, programmers can write more dynamic and flexible code by utilizing the methods provided by the type. Now, let's explore an example of abstraction in mathematics. Let's consider the concept of a set. We usually think of a set as a collection of objects. However, these words object and collection is very ambiguous. If we define a set in this way, we encounter paradoxical statement like Russell's paradox. Russell's paradox is a statement about the set that contains all sets that do not include themselves as an element. There is no answer to whether this set includes itself, because if it includes itself, it must not include itself, and if it does not include itself, it must include itself. An easier example of such paradoxical statement is the sentence such as, "This sentence is false." Whether you assume this statement is false or true, you always reach a contradictory conclusion. In mathematics, such paradoxical statements are not allowed. Therefore, mathematicians have developed clear axioms that do not use ambiguous expression to define sets. These are called set axioms, and they specify what can be done with sets. Let's look at a few examples. First, the axioms of extensionality states that two sets are equal if they have the same elements. This means that equality can be determined by comparing the elements of two sets. The axiom of union states that the union of two sets is also a set, indicating that we can form the union of two sets. In this way, mathematical axioms define what a mathematical object can do rather than what it is. These axiomatic definitions are used elsewhere. Let's now examine the definition of natural numbers. To define natural number, we need to look at what can be done with natural numbers. Natural numbers are numbers used for counting things. To count, the objects being counted must have two properties. First, each object must be distinguishable from one another. And second, they must be able to be ordered sequentially. Therefore, natural numbers must themselves be distinguishable and have the ability to be ordered sequentially. Since natural numbers are the first number to be defined, there are no number before them. Therefore, natural numbers must be defined in a situation where there is nothing. Here, the concept that can be used is the empty set, which means there is nothing. Hence, natural numbers can be defined as follows. First, 0 is defined as the empty set. Next, 1 is defined as a set containing the empty set. Then 2 is defined as a set containing 0 and 1. Continuing this process, all natural numbers can be defined. Of course, to define the existence of infinitely many natural numbers, the principle of induction must be used, and other set theoretic axioms are required to define their operations such as addition. The important thing is we can distinguish the natural numbers with the set theoretic definition and order them through the inclusion relationship among sets. Another example is the concept of real number. We typically understand real numbers as a number that exists somewhere on the line. However, with a slight reflection, we realize that this definition doesn't truly convey the nature of real numbers. Real numbers are also defined through axioms. The axioms used here can be classified into four categories: the axioms on addition, the axioms on multiplication, the axioms on order, and finally the axiom called completeness of real numbers. I will omit a detailed explanation of these axioms here. The important thing is that anything that satisfies these axioms can be called as real numbers. Now, how is abstraction used in programming languages? The purpose of programming languages is to process data. Therefore, the concept of data type is very important. However, some programming languages support not only static types but also abstract types. These abstract types are defined by a set of functions called methods. Using abstract types, programmers can focus only on what the type can do without concerning what they are. Let's look at an example in Go programming language, a language that supports abstract types. Suppose we want to define an abstract type called element with the capability to compare equality and difference with other types. In Go, abstract types are called interface. Here is how we can define such abstract types in Go syntax. Type element interface with the name equals with the input type any and output type boolean. With this definition, any type has a method name equals with the same input and output types can be treated as an abstract type element. Let's define another abstract type called finite, which means that it has a finitely many elements. If the number of elements is finite, we must be able to count them, and thus we need a method called len. The len has no input and returns the number of elements as an integer type. Any type with method of this form and name can be treated as a finite interface. Abstraction plays a crucial role in both mathematics and programming languages. Let's compare its roles side by side. Defining an object in mathematics is similar to defining a type in programming languages. In this case, consider the type as an abstract type. All mathematical objects are fundamentally based on a list of axioms. These axioms define what the object can do. In programming languages, abstract types are also defined by the methods that defines what the types can do. Finally, the mathematics computes invariants such as volume or discriminants based on the definition of the objects. In programming languages, functions are written to compute things with the types defined in its way. Our goal is to reinterpret abstract mathematical concepts, specifically geometric ones, as abstract types in programming languages by specifying its axiomatic roles. There are two reasons why this is necessary. First, it is to show that the mathematical abstraction is closely related to engineering thinking. Second, it is to explore the somewhat rigid process of mathematical abstraction using flexible programming languages. Furthermore, this process will propose a new way to construct or structure and understand mathematical concepts. We will use the Go language, and in the next video, we'll introduce the Go language and abstract mathematical concepts one by one to express them in Go. Thank you.